All right, problem 15 solved. When a .045 kilogram golf ball, all right, so 45 grams or mass of the golf ball is equal to 0.045 kilograms. Takes off after being hit. Its speed is 41 meters per second. So let's assume that it's at rest when we first hit it. Otherwise, it'd be a very exciting game of golf. All right, so then its final velocity is 41 meters per second. How much work is done on the ball by the club? All right, so that's part A. How much work is done on the ball by the club? This, again, is just a work-energy relationship. So to find the work done on the ball by the club, we have to find its change in kinetic energy. All right, so assuming, as we said, that it starts from rest, that means its initial kinetic energy is 0. So work is going to be equal to 1/2 mv final squared. So just plug its stuff in. Work is equal to 1/2, and the mass is 0.045 kilograms, times its final velocity, 41 meters per second. Whole thing squared there. And then that gives us a grand total of work is equal to our final kinetic energy, which is going to be equal to 37.8 kilogram meters squared per second squared is joules. Straightforward application of work-energy theorem. All right, now part B asks us, assuming that the ball and club contact the ball for a distance of 0.01 meters and that the force and the displacement are parallel, ignoring the weight of the ball, determine the average force applied to the ball by the club. What do they mean, ignoring the weight of the ball? Well, if we've got a ball on a tee here, all right, there's the grass, and this thing takes off like this, and the force and the velocity are in this direction, well, really, we have a net force that includes the force exerted by the club as well as this little teeny weight of the golf ball. But it's saying to ignore that because, let's just go ahead and erase it because they say to. Why would we be able to do that? Only because the weight of the ball is so small compared to the large force exerted by the club on the ball when it hits the ball. All right? So we're just going to make this smaller so we won't forget it. But let's go ahead and do part B. And part B says, what is the average force? Well, if we know that the work done is equal to, this is what we have up here, the change in kinetic energy, all right, and which is equal to our final energy, all right, we also know that work is equal to FD cosine theta, all right, now we've already said that theta is equal to 0, theta is 0, so cosine theta is 1. We decided, or we assumed that the force and the displacement were parallel. All right, so given that, what is the average force? That means that the average force is going to have to be equal to the work over the distance that it's over which it's done. All right, and so our work from right here was equal to kinetic energy, our final kinetic energy, so it's going to be kinetic energy over distance. That means our force is going to be equal to kinetic energy of 37.8 joules divided by our distance, 0.010 meters. Get our significant figures in there. So that's the same thing as multiplying by 100, isn't it? So you got 37.8, so we go 1, 2, 0, 0. That would give us 37, whoops, that's an 8. 3780 joules given the sig figs that we have. So let's check that dimensionally. And I'm sorry, that would not be joules, would it? Good thing we're checking dimensionally because that seems like it should be newtons if we're looking for a force. But let's just make sure we know that joules per meter will be, a joule is a kilogram meter squared per second squared divided by meters. That would give us, this n cancels out one of these, which gives us kilogram meters per second squared, and that is in fact newtons, not joules, Mr. Culbertson. And so that gives us our final answer there.